We continue with surface integrals, and in this example we're making like an introduction to the divergence theorem. So as an example, let's take a very simple function. For example, it could be x squared, y squared, z, and let us be the unit sphere. We want to compute the surface integral of f over the sphere, and since we introduced the orientation of the surface already, so now I'm telling you where n is the outward normal vector. So now we started focusing on the orientation of the surface, and remember when we say the orientation of the surface, that is using the normal vector. So basically my surface is a sphere. We're asked to find the integral with this normal vector, the outward. So what do we mean by the outward normal vector? You go to every single point on the sphere in R3. At each of these points there is a normal vector. The normal vector could be outward the surface or inward the surface. In this example, we're not interested in this. We are interested in the outward normal vector. So as a surface integral, we start by finding the parameterization of the sphere. And remember, the parameterization is the spherical parameterization. So it is sine phi cosine theta, sine phi sine theta, cosine phi. Also, we already computed in one of the examples, we already computed r theta cross r sub phi, and we found it to be minus sine squared phi cosine theta, minus sine squared phi sine theta, and minus sine phi cosine phi. Now, before doing any of the other computations, because in this example we're interested in the outward normal vector, so we want to test if this normal vector is the outward one. So how do we test that? To do this, we take points. So in general, how do we test the orientation or the direction of the normal vector? You take any point on the sphere and you compute the normal vector at that point. So for example, we have this sphere. We take a point on the sphere. Let me call it P. How do you find points on the sphere? Of course, you can look back at the equation of the sphere. Remember, the equation of the sphere is x squared plus y squared z squared equals 1. So you can select a point by finding an x, y, z that satisfies the given equation. Alternatively, and easier, is to plug certain values for theta and phi. So I know that the theta values are from 0 to 2 pi, that represents this orientation. And the phi values are from 0 to pi, that represents this orientation. So for example, if you select theta equals phi, and both are pi over 4, that gives you the point, so you plug in the original parameterization here. So if you select phi and theta pi over 4, this gives you half, another half, and 1 over root 2. And I'm going to say this is by selecting theta and phi both equal to pi over 4. So this is my point. Now at this point, at P, you find r sub theta cross r sub phi. That's the normal vector we found here. So if you take this vector and you substitute the theta and phi values, what do you get? You get minus 1 over 2 root 2 minus 1 over 2 root 2, and minus half. So this is my point, so this is my point, and this is my normal vector. Now let's see, now what is my concern? My concern is this the outward or the inward normal vector? When we say outward and inward, that makes a lot of sense, because in this example we're dealing with the unit sphere, which is a closed surface, and it makes a lot of sense to say outward or inward, the sphere. So how do we tell if this is the inward or the outward? This is the x-axis, the y-axis, the z-axis. So the way we do it, we plug our point. So the p is half 1 over root 2. That means the x is positive, the y is positive, the z is positive. So my point is somewhere here in the first octant. This is my p in the first octant. Okay, after plotting the point, we plot the normal vector. We draw the normal vector starting at that point. So this is my normal vector. We say, okay, so the x is negative, that means you are going in the opposite way. The y is negative, you are going in the opposite way. And the z is negative, we are going downward. So if you draw that normal vector, roughly, it will be pointing that way. If you shift this normal vector and you draw it exactly at P, it will be inward the sphere. So at this stage we decide, okay, so this normal vector, this r sub theta cross r sub phi, is the inward normal vector. And this is not what we are interested in. So in my case, because we are interested in the outward normal vector, remember, so in my case, we take the normal vector as r sub phi cross r sub theta, and then okay, so what is my normal vector? We just go back to the this normal vector and we multiply it with negative. So it will be sine square phi cosine theta, sine square phi sine theta, and sine phi cosine phi. And now we are ready to do the surface integral. So this is double integral. Of what? We substitute the parameterization into f, then dot the normal vector, d theta, d phi. The phi values are from 0 to pi. The theta values are from 0 to 2 pi. Now what was my function? My function was here, x squared, y squared, z. So we go back to the parameterization. X was, from my parameterization, it was sine phi cosine theta, but the function says x squared. Then y squared, the y was sine phi sine theta. Again, we have a square. Then the z was just cosine phi. Dot the normal vector. Now this is my normal vector, so it is sine square phi cosine theta, sine square phi sine theta, and sine phi cosine phi. Now we do the dot product. Now clearly, when you just quickly, when you make the dot product, you multiply this component with this component. From these two components, you get cosine cube. Now, when you get cosine cubed, what's the integral of cosine cube from 0 to 2 pi? It will be 0. The same for this, it will give you sine cube, and that will be 0. We discussed these in details earlier. So now what's left basically in this example is just sine phi cosine square phi d theta d phi. So this is what's left after doing the integral. And now this is an easy integral. So here you don't have any theta. So the first integral gives you 2 pi. The integral from 0 to pi sine phi cosine square phi d phi. And now this one, you can do it using substitution. So if you substitute cosine phi as t, it will give you minus cosine cube phi over 3 from 0 to pi. And what is this? So this is negative 2 pi over 3. You substitute the pi, cosine phi, when phi is pi, that's negative 1 cube, negative 1, minus the 0 gives you 1. So basically, This is 4 pi over 3. 4 pi over 3. We're dealing with a sphere. Remember, my surface was a sphere. We got 4 pi over 3. Does this remind us of any quantity? Yes. What is this? This is exactly the volume of the sphere. So is it a coincidence? So my question is this the volume of the sphere? Is it really the volume? How did we get this number? Yes, it is the volume. But I mean, like, is there any relation between this surface integral and this sphere? In fact, yes. And this question, in fact, leads to our new title, which is the divergence theorem. So this will be our next topic.